Now we continue the discussion on related rates with example 4. A conical water tank with vertex down has a radius of 3 meter at the top and is 6 meter high. If water is being pumped into the tank at a rate of 3 meter cubic per minute, find the rate at which the water level is rising when the water is 2 meter deep. We will use the procedure given in the related rates part 1, okay, to solve this question. Alright, so if you look at this one, okay, given in the question is the rate of water being pumped, it is 3 meter cubic per minute. If you look at this one, it is represent the volume. So we have the volume as dV over dt is equal to 3, and we want to find the water level rising, okay, the rate of water level rising, so we need to find the H over dt. So in step 2, we should have an equation that relates V and H. But if you look at this one, okay, the volume for a cone is given as 1 over 3 pi r squared h. We have the V in terms of r and h. And how are we going to eliminate the r so that we can only have the V in terms of h only, alright? So if you look at here, okay, this is a triangle related to the cone, alright? It is 3 meter radius on the top and 6 meter high of the cone, alright? So if you look at this one, the ratio between the R and H is 3 over 6. And if we write, we can write R is equal to H over 2. And if we replace R is equal to H over 2 in this equation, in this formula for volume, we will get as V is 1 over 3 pi H squared over 2 squared H, or pi H cubic over 12. So we already get V in terms of H. So that represent the variable in step 1 and step 1, V and H. Okay, next step, we find the, we differentiate both sides, implicit differentiation, we get dV over dt. We differentiate this one, get 3 pi H squared divided by 12, dH over dt. Okay, alright, if we simplify it, we can write as d over dt is equal to pi h squared over 4 dh over dt. Okay, now we substitute dv over dt is 3 and the h is 2 meter deep. We replace h with 2. Okay, so we get towards the end, dh over dt is 3 over pi, or it is equal to 0.95. Therefore, the water level is rising at the rate of 0.95 meter per minute. Now we go to example number 5. An ice cube in the shape of a cylinder as shown in figure here. This is a figure shown with the an ice cube, okay, in the cylinder shape, is melting at a constant rate of 4 cm cubic per second. We want to find the surface area of the ice cube in terms of R, and also the volume of the ice cube in terms of R. And number 3, then we need to find the rate of change of the surface area of the ice cube when the radius is 2 cm. Alright, now we look at the first part. We want to find the surface area of ice cube in terms of R. So the surface area is given as 2 pi r squared plus 2 pi rh. Alright, this is the given formula for surface area of cylinder. Okay, if you look at here, we have h. H in this case is r plus 4, so we will substitute r plus 4 here. Alright, so therefore we get this one, and after we expand, we get this one, and lastly we get s is equal to 4 pi r squared plus 8 pi r. Okay, now we go to question number 2. We want to find the volume of the ice cube in terms of r. Alright, so we know the formula for ice cube is volume is V is pi r squared h. We replace the h with r plus 4 and we expand it. So we get the volume is pi r cubic plus 4 pi r squared. Now we move to the third example. The third question is to find the rate of change of the surface area. Okay, we want to find the rate of change of the surface area when the radius is 2 cm cubic. Okay, so if you look at here, given here is the melting at constant 4 cm cubic per second. So this is the dV over dt. Alright, so dV, and we want to find the S over dt. Alright, so if you look at here, dV over dt is negative because it is melting. The volume is decreased. Alright, we want to find ds over dt. Okay, actually we must have a formula that relates V and S, but we don't have that. But we only have V in terms of R. Okay, we just use this one. Even though it does not follow the step 1 procedure, we just use the volume we get from the previous slide. Okay, we differentiate it implicitly, both respect to time, the left and the right, so we get here. Okay, dv over dt is equal to differentiate pi r cubic, we get 3 pi r squared dr over dt, 8 pi r dr over dt, and if we factor it, we get dv over dt is equal to 3 pi r squared plus 8 pi r dr over dt. Okay, if we substitute V dv over dt is negative 4, r is equal to 2, so we can find the dr over dt here. So we get dr over dt is negative 4 over 28 pi, or negative 1 over 7 pi. Okay, but here we want the ds over dt. But we want to find the ds over dt. Alright, we want this one actually. Alright. So from the previous slide, we can write s in terms of r. So we get s is equal to 4 pi r squared plus 8 pi r. So we differentiate it implicitly with respect to time. So we get here ds over dt, differentiate 8 pi, we get 8 pi r dr over dt plus 8 pi dr over dt. And if we factor, we can get 8 pi r plus 8 pi dr over dt. Then we replace the dr over dt and r. So dr over dt we get from here, we get negative 1 over 7 pi, and r is 2. So therefore we get ds over dt as negative 24 over 7, or negative 3.42. Therefore, the surface area is shrinking or decreasing at the rate of 3.42 centimeter squared per second. Now we go to the example 6. Okay, a 15-meter ladder is leaning against a vertical wall as shown in the figure below. Alright, this is the figure. If the bottom of the ladder is pulled away from the wall at the rate of 2 meters per minute, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 9 meters from the wall? Okay, if we pull away the bottom of the ladder, alright, so you can see that the top of the ladder will go down. Alright, so we want to find the rate of change of the top of the ladder sliding down. Okay, if you look at this one, okay, we can write an equation based on the ladder and the wall here. We assume the wall as the y, the floor as the x. So we can write an equation x squared plus y squared is equal to 15 squared by using Pythagoras theorem. Alright, now we want to solve. Okay, so if you look at here, given in the question is pull away from the rate of the ladder is pulled away from the wall. You can see that the x is away from the wall. Okay, so we write dx over dt is 2 meters per minute, and we want to find the dy over dt, where x is the distance from the base on the wall to the foot of the ladder, and y is the distance from the wall to the top of the ladder. Okay, so this is the plotted. Okay. Alright, so this is the formula that we have written in the previous slide. Okay, we get that one. Okay, and if we differentiate implicitly, we get x squared, we get 2x dx over dt. We differentiate implicitly with respect to time. 2y dy dt is equal to 0. And we replace at x is equal to 9. Okay, when x is equal to 9, we get y is equal to 12 here. So we substitute in the step 4, we substitute the y, x, and dx over dt. So we get this one. And lastly, we get dy over dt is equal to negative 36 over 24, or negative 1.5. Okay, it means that the top of the ladder sliding down, because it is negative, sliding down the wall at the rate of 1.5 meter per minute. So it means that if we slide away the x at the rate of 2 meter per minute, so the y will go down at the rate of 1.5 meter per minute. Okay, now this is the first example. on the related rates. You can try it at home. And this is the second example. Also, you can also try it at home. Okay, that's all for this lesson.